Well, it's a great pleasure for me to be here at this great university, addressing this meeting of the Mexican Physical Society on a question of quantum information that we're seeing more and more in the news these days. And so I'm very happy to have the opportunity to tell you a little bit about this idea of quantum information, what I've called a scientific and a technical revolution for the 21st century. Now, I should say, as one must at the beginning of talks like that this work has been supported over the years by my institution, NIST, and by the Office of Naval Research, DARPA, and the National Science Foundation, which supports a Physics Frontier Center at the Joint Quantum Institute, where I work, which is joint between the University of Maryland and NIST and the Laboratory for Physical Sciences. And I want to take a little moment to do some shameless advertising for young students who might be at a position in their career where they're thinking about continuing their education or their research. We have lots of opportunities for further study and research at the JQI. Graduate and postdoctoral fellowships and lots of opportunities. And so I encourage any of you young people who are at that stage of your career to consider the Joint Quantum Institute. Well, let's come back to the topic of today's talk, quantum information, a scientific and technological revolution for the 21st century. So what is quantum information? Well, before I tell you, I want to begin with a little bit of a warning. This is not going to be a talk for the experts. And so for those of you who are experts, and I know there are some of you in the audience, I want to apologize before I start for the fact that I'm going to commit many sins in the process of giving this talk in oversimplifying any number of things. And I just hope that you'll forgive me in advance for all the sins that I am about to commit. Okay, quantum mechanics and information science were two of the most important and really revolutionary developments of the 20th century. At the beginning of the 20th century, we had the development of quantum mechanics, which really changed our understanding of our natural world in a really fundamental way. Not only did it explain all kinds of things that couldn't be understood about the microscopic world, it really changed our views of the nature of reality. So this was a really fundamental change in physics and the way we think about things. The information revolution has been similar. The rise of computers that can do tasks that used to be only done by human beings has changed the way we think about thinking. And now what I'm claiming is that in the 21st century, we have a convergence of these two revolutions of the 20th century in a new revolution, a new science really, for the 21st century, that is quantum information science. So in order to understand the significance of quantum information science, let's go back a little bit while I dig into my briefcase. You see, I had a wonderful afternoon talking with some students in a rather noisy restaurant, and I was shouting most of the time, so I'm afraid that my voice may be a little bit scratchy. So I'm going to take a cough drop and hope that this will help my voice a little bit. Okay, what's the classical quantum revolution all about? Well, classical mechanics has been around for a very long time. Newton taught us the rules of classical mechanics, and that explains all kinds of things. The motion of the planets, the behavior of billiard balls. I wonder why it is that physicists always like to talk about billiard balls. It's not like any of us actually play billiards, but we love to talk about billiard balls as being the quintessential classical mechanical object. Well, anyway, it explains that, and it led to things like the Industrial Revolution and all sorts of machines, engines, automobiles, and all kinds of other everyday stuff. We can thank classical mechanics for all that stuff. I recently attended a meeting in Gothenburg in Sweden about quantum information. And you know, the way these meetings often work, we had an excursion. We went out on a 19th century steamboat out onto the harbor of Gothenburg. And knowing that there were a bunch of physicists on board, they invited us down into the engine room of the steamboat. And this is a picture in the engine room of that steamboat. Let me run the movie. It's really such a marvelous thing to see all these things going on. You know, I think of this as being the pinnacle of the achievement of classical mechanics. All of these pistons and rods and gears going around, all of this was explained by classical mechanics and put to very good use. But when you think about it, classical mechanics does not tell you why those metals are hard, why glass behaves the way it does, why any number of material properties are what they are. No one really thought about that when they thought that classical mechanics was explaining everything. There were a few little things about the spectrum of the black body radiation that they thought was a problem, but the fact is, we didn't understand anything about our natural world. We couldn't explain the nature of materials with classical mechanics. We just didn't realize it. And then came quantum mechanics in the 20th century. People like Niels Bohr, Schrödinger, explained the behavior of atoms and molecules. Before the 20th century, not everyone even believed that matter was made up of atoms and molecules. But as that became more and more of a widespread understanding of the nature of things, it became necessary to explain the behavior of these atoms and molecules, and it required a whole new science, and that science was quantum mechanics. And what came of it was something just as profound as what came from the classical mechanics revolution. That industrial revolution changed our lives in fundamental ways, and quantum mechanics did as well. It gave us all sorts of things like semiconductor electronics. Almost everything that we think of as being a feature of our modern life, our cell phones, our computers, our televisions, rely on quantum mechanics to have been made to understand how they work at all. All these things are the fruits of quantum mechanics that came to us in the 20th century. All sorts of things that today are everyday things and amazing things. So what is this quantum mechanics all about? Well, it describes the behavior of the submicroscopic world. One of the things that quantum mechanics tells us is that every object has a wave-like nature that's described by this relationship that we call the de Broglie wave relationship. In other words, that the wavelength of some object is equal to Planck's constant divided by the momentum of the object. The momentum is just its mass times its velocity. Now, Planck's constant is a really, really small number. It's 6 times 10 to the minus 34 joule seconds. So when you think about it, what that means is that for any reasonable object, the wavelength associated with it is going to be so incredibly tiny that you can simply forget it. The wavelength of a billiard ball, we're back to billiard balls again, is something on the order of 10 to the minus 30 meters. Now, let me give you some idea about how small 10 to the minus 30 meters is. This is a meter, approximately, right? The size of the nucleus of an atom is 10 to the minus 15 meters. So we're talking about something that is smaller compared to the nucleus of an atom than the nucleus of an atom is compared to a meter. That's really, really small. In other words, you can forget about it. It just doesn't matter. On the other hand, if you ask what is the wavelength of an electron in an atom, that size is about the size of the atom. And so you'd better take into account the fact that electrons behave like waves if you want to understand atoms. You don't need to do it if you want to understand billiard balls. But if you want to understand atoms, you must take into account the fact that those atoms behave like waves. And that wave nature of matter explained all sorts of things and led to most of the things that we think of as being modern technology. Semiconductor electronics, all of that depends upon understanding the wave nature of electrons. But while that understanding was incredibly useful, and continues to be incredibly useful, it's not the whole story. There are some really weird aspects of quantum mechanics that I'd like to tell you about now. Think about an electron. So we all have this picture of an electron going around an atom. It's a completely bogus picture. It's totally wrong. The electron doesn't go around the atom. It's some sort of a cloud that encircles the atom. But we still carry in our minds this image that came to us from Niels Bohr of an electron going around an atom. And the electron is like a little spinning top. And we can detect that spin and we can detect its effects. But think about this. The size of an electron, and we know this both from theory and experiment, the size of an electron, the diameter of an electron, is 0. 0. We've measured it very carefully, and the measurements are consistent with 0. The best theory that we have tells us that the size of the electron is 0. How does something that has 0 size spin? I don't know. I mean, I can write down the equations, it's all perfectly reasonable. And a little bit of water may help my throat, although the cough drop is doing a good job too, but thank you very much, that's very kind. So that's already a bit of a mysterious thing, the fact that something with 0 size can spin, but it gets a lot more weird than that. If you had a spinning top, you could turn the direction of that top in any direction you wanted. You just grab a hold of it and turn it. It would feel a little bit strange. If you've ever handled a gyroscope, you know that it's a little bit strange when you try to turn it around, but you can turn it in any direction you want. And what that means is that the amount of spin there is along any direction can be anything you want it to be. But with an electron, that's not so. Once you pick an axis, it turns out that the electron can either be spinning with one way around that axis or the other way around that axis. In other words, it can either be this. Oh, wow. It's all of a sudden started to work. It can either be spin up or spin down. Those are the only two choices that are available to the electron. Why is that? Well, again, I have no explanation, although I can write down the equations that show that it's true, that this electron can be in just one of two states. Just one of two states. But here comes the really weird part. It can be in both states at the same time. Now, we are very fond of saying things like, well, you can't be in two places at the same time. But in quantum mechanics, you can. So, when I said that quantum mechanics changed the way we think about reality, this is part of what I mean. That the common notions of reality, you can't be in two places at the same time. Something has to be either spin up or spin down if those are the only two choices. Not true at all anymore. How can that be? Well, again, my friends, I have no good explanation other than to say I can do the math, and you could too. But let's get a little bit of an idea. Look at this cube. You've seen cubes that are like this any number of times, and when you look at it, you see that you can make it change sort of in your mind to be one of these two kinds of cubes that have this face be the face that's out, or it could be this face that's the face that's out. A little hard for me to draw this with my cursor, but you get the idea that once you look at that, you sort of make it be one thing or the other. And that's sort of the way it is with a quantum mechanical object. You start off with something like this that is ambiguous, and then when you look at it, it's one thing or the other. But before you look at it, it's both things at the same time. Now, I want to caution you that This is not a very good analogy. There is no good classical analogy to the weird stuff that happens in quantum mechanics, but this is an attempt to show how it might be possible for something to be in two different states at the same time. This picture is ambiguous, and in a certain sense is both this and this at the same time, but when you look at it carefully enough, you'll make it be one or the other, and that's sort of what happens in quantum mechanics. Now, it gets worse. We have superposition, that one particle could be in two different states at the same time. But when you have two particles, this idea of superposition starts to get really strange. Let's imagine that we have two particles called 1 and 2. Okay, so there's 1, there's 2. And let's say each of those particles is something like an electron, so it can be spin up or spin down. So let's make a superposition of the state of the two particles together. And that state is going to be that particle 1 is up and particle 2 is down, and at the same time, particle 1 is down and particle 2 is up. Now, this is what physicists call an entangled state. And the definition of an entangled state is one where I can't describe the state of the two particles, described here, as being the product of the state of one particle times the state of the other particle. What it means is that what happens to one particle is entangled with what happens to the other particle. In other words, if I measure particle 1 to be up when I look at it, then I know that particle 2 is going to be down. But if I measure particle 1 to be down, then I know the particle 2 to be up. In other words, the fate of the particles, when I look at them, is entangled with the fate of the other particle. That's what we mean by entanglement. And this is really a weird aspect of quantum mechanics. Now, it really gets strange when we separate the two particles. So let's imagine we've got these two particles that I've been talking about. Spin up, one of them is spin down. They're in this superposition. And we send one of the particles to the left and one of the particles to the right. Now, the particle that goes to the left might be spin up or spin down. And the same is true of the particle going to the right. And there's no way that anybody could possibly know, when you measure it, whether the particle going to the left is up or down. It's just the nature of the state that it's both up and down at the same time. You're going to measure one or the other things when you measure it. But there's no way of predicting what it's going to be beforehand. But here's the weird part. If this one turns out to be up, you know that this one is going to be down. And in principle, that thing could be on the other side of the laboratory. It could be on the other side of the world. It could be on the other side of the universe. And you instantly know, if this one, okay, come on, this is supposed to work. It was working so well before. You know, all that stuff about how semiconductor electronics is so wonderful. Yeah, as long as it works. Okay, here we go. So if this one is up, then this one is surely going to be down. And this one, if this one is down, this one is surely going to be up. How does it know? How does it know when it's that far away? Now, those of you who are experts know that I'm telling lies now. Because if I, in fact, measure up and down along the same axis here and here, then there's nothing very strange. But if you start changing the direction along which you make the measurements, you can prove that quantum mechanics predicts something that is completely at odds with common sense. Common sense would tell you that, what happened here? Okay, let's go back. What? Good heavens. Okay, let's go back here. Okay, so common sense would tell you that before you measure it, that its state, in some sense, existed, and you just have to measure it. And that everything that you know about what's going to happen here could be figured out on the basis of the stuff that's going on in the vicinity of where you're going to make the measurement. That seems perfectly reasonable, right? And if you take that point of view, you can calculate the possibility of how the measurement that you get over here could be related to the measurement that you get over here. And then you find that quantum mechanics violates that by a lot. In other words, you just take ordinary common sense, calculate how correlated those measurements could be, and you find out that quantum mechanics predicts a correlation that is much stronger than could ever be the case if common sense prevailed. So then you do the experiment and you find out common sense does not prevail, and in fact the world is strange. Einstein recognized this back in 1935. We call this the Einstein-Podolsky-Rosen paradox. John Bell in the late 1960s figured out this, the mathematics behind it, and showed that quantum mechanics is really deeply strange. Einstein had this deep understanding that told him that quantum mechanics was really strange, but it took John Bell to explain it to the rest of us, to make it clear that Einstein was right, and that his discomfort with quantum mechanics was something that was deeply rooted in simple common sense. So this idea of entanglement is one of the really weird aspects of quantum mechanics, and something that people didn't think about until Bell came along. So here's the picture of entanglement that I like to present you. Again, a poor representation classically. Let's say that I had two boxes that are these ambiguous boxes. I'm not sure about you, but when I look at those two boxes, I almost always see them the same way. That is, I can't make the box on the left point differently from the box on the right in my mind, so that I see something that looks, now my electronics isn't working again. But you know, I see something that looks like that set of boxes on the left or the set of boxes on the right, and yeah, technology is great. Okay, so again, the result that your mind gives you for these two boxes is entangled. When you see this box with this face forward, then you're going to see this box with that face forward. At least that's what happens in my mind. So again, it's not a good analogy, but it's the best we got, because the quantum world really is strange, and we have no way of making good analogies in the classical world with the things that happen in the quantum world. So now we are here in the beginning of the 21st century, and what I'm here to tell you is that while the 20th century was mainly dealing with the wave nature of particles and pretty much ignored this weirdness that I've been talking about, this idea that things can be in two places at the same time, that something can be pointing both up and down at the same time, that what happens on one side of the world can be correlated with what happens at the other side of the world in ways that common sense says is impossible, that all these weird aspects that weren't part of the 20th century technology are now becoming part of the 21st century technology, and I and others have called this the second quantum revolution. And in particular, it's intersecting with information science in a really wonderful way. Quantum computers, and I'm going to tell you a little bit more about what quantum computers mean. But if we can make a quantum computer in which we do information processing with these weird aspects of quantum mechanics, that quantum computer is going to be more different from today's high-speed digital computers, like this one. It's going to be more different from this high-speed digital computer than this computer is from the ancient abacus. So let's see how that works. Let's talk about quantum information and compare it to classical information. Now, as I think most of you know, inside your computer, information is stored in binary code, zeros and ones. That's what stores all the information and what allows the processing of the information inside your computer. A classical bit that is either 0 or 1. And those bits have a physical embodiment. It's a transistor that's turned on or off. It's a spot on a compact disc or a DVD or a Blu-ray that is either burned or not burned. It's a spot on a magnetic hard drive that is magnetized in one direction or another. And one of the great powers of digital information is the sureness with which we know that a bit is either 0 or 1. The transistors aren't half on or half off. The spots on the CD are not half burned. They are very firmly one thing or the other. And this is one of the great features of digital information. And that's the way things work today. Now, just in case you're wondering about digital information, there are two kinds of people in the world, as always, right? Okay. Quantum bits, on the other hand, are things that could be 0 or 1, but they can be both 0 and 1 at the same time. So imagine something like the electron that we've been talking about before that might be spin up, or, well, spin down or spin up. We could call that 0 or 1. But as we saw, the electron can be both up and down at the same time. In other words, if we used an electron as a quantum bit of information, it could be something that is both 0 and 1 at the same time. Now, why would you want to do such a thing? The power of digital information is that you're sure that something is either 0 or 1. And now I'm telling you, let's think about a new kind of bit of information, a quantum bit, that can be both 0 and 1 at the same time. That sounds really, really stupid. Because I want to know what my information is, and I'm telling you, well, what if we accept complete ambiguity about what the information is? What good is that possibly going to do? Well, let's think about that for a moment. Let's imagine that we have some classical bits. Here's a register of 3 classical bits, and in that register I can store any number from 0 to 7. This is 5. 101 is 5 in binary code. So that's great. I've got 3 bits. I can store any one of 8 numbers from 0 to 7. Quantum mechanically, if I make each one of these things a qubit, that is a quantum bit, something that can be both 0 and 1 at the same time, then this register could have a superposition of all of the 8 possible numbers. Here's a mathematical representation of the thing, and so there could be all 8 numbers at the same time stored in this single 3-qubit register. In general, this kind of a state is what we've called an entangled state before. Okay, so with a classical register, one number of 8 possible numbers. With a quantum mechanical register, all 8 numbers at the same time, and in arbitrary amounts. Let's say that that was a 300-bit register. Well, if it was a classical register, then I could store one 300-bit number. It's a big number, but it's not, not necessarily that huge. But if I ask instead for what the quantum register can do, it can store 2 to the n, all possible n-bit numbers. There's 2 to the n such numbers. If that n is 300, then the number of different possibilities that could simultaneously be stored in that register is greater than the number of particles in the entire visible universe, with just 300 bits. Your computer might have a terabyte in it. And I'm saying that if you had a quantum computer with a register with only 300 bits, that it could store at the same time more numbers than there are particles in the entire universe. That scaling is one of the things that gives quantum computing its power. Now, we don't have quantum computers that can do this yet, but we're hopeful. And if we had such quantum computers, this kind of scaling will allow us to solve problems that are otherwise insoluble. Here's an example of a hard problem, factoring large integers. So look at this number. I don't think any of you can, in your mind, figure out what the prime factors of that number are. On the other hand, any primary school student could multiply these two 3-digit numbers, which happen to be prime, to get this number. The fact that it's easy to multiply and hard to factor is really important for every one of you because of something called public key encryption. Let's say you go to your favorite website, and when you want to buy something, you decide what it is you want to buy, and at some point you put in the information about your credit card. Now, the company that you're buying this from is assuring you that the transmission of your credit card information is going to be completely secure. How does it do that? Well, you can't see it happening, but what's happening is they are sending you a big number, much bigger than this one, okay? And then you're doing something with that number, multiplying it and doing some operations that your computer is all doing this in the background to your credit card number and sending it back to the company that's going to charge your credit card for that. Because they know what the factors are, they can decrypt that and see what your credit card number is. But because nobody else can know what the factors are, because it's so hard to factor a big number, they can't figure it out. So this is what we call public key encryption. The asymmetry between how easy it is to multiply and how hard it is to factor allows you to send information to some company that you're buying material from in a completely secure way. And it all works because it's hard to factor numbers. In fact, it's exponentially hard to factor numbers. The time it takes to factor a number using a computer grows exponentially with the number of digits. So if computers get faster, all you have to do is add one digit to your big number, and then the computers won't be able to do it anymore because it'll increase the time by a lot, and then the computers won't be able to do it. So people use this all the time. You use it even though you don't see it transparently. Every time you buy something online, people in the military and diplomatic services use it all the time to transmit messages. Now here's the thing. There is an algorithm called Shor's algorithm that can factor numbers quickly if you had a quantum computer. This is really weird. This is really wonderful. What it means is that by changing the hardware with which you solve a problem, you change a problem from a hard problem to an easy problem. And that's never been done before. And yet, Shor's algorithm allows it to happen. And this is one of the reasons why people have gotten really excited about quantum computing. The people who got most excited about quantum computing are the spies, because they rely on this kind of public key codes to transmit secrets, and they would love to be able to decrypt the messages of their enemies, and they can't because they can't factor numbers. And if they had one of these machines, they could. So the first people to give a bunch of money to do research on this have been the spies. And this captured people's imagination to the extent that people wrote science fiction books about the possibility of making a quantum computer. So here's a Tom Clancy novel where the evil protagonist of the story says that using Shor's algorithm, that he can factor a large number with a quantum computer in a small fraction of the time that the same number would take using a supercomputer. And they obviously did their research for this thing. They say down here that Wineland and Monroe, so these are two friends of mine, worked out some of the early ideas of quantum computing using trapped ions. Now, Dave Wineland and Chris Monroe were at the National Institute of Standards and Technology, my institution, out in Boulder, when they did this work together. Today, Chris Monroe is at the Joint Quantum Institute, where I work now, and so it's very nice to see them mentioned in this book. The evil protagonist goes on to talk about how he came to be able to make a quantum computer. He says it's not something that you whip up in a mayonnaise jar, that people have been working for a long time trying to do it with ion traps and optical traps and NMR. It's all here. All this is true. And he again talks about how Wyland Monroe worked it out and how other people, and then his colleague asks, well, how was it that you were able to succeed when all of these other people didn't succeed in making a quantum computer? And he says, because I'm smarter than they are. Now, I know Wyland and Monroe, and when he says he's smarter than they are, that's what makes it fiction, okay? But anyway, the point is that it's not just science fiction. That quantum information and computation isn't just fiction. There's a lot of research going around all over the world, and there's big national and international investment. The European Union is investing billions of euros. The Chinese government is investing tens of billions of dollars. The US government has plans to invest a couple of $1 billion in this. This is a big deal. And countries all over the place are doing this in laboratories all over the world. Why is that? Well, there are a lot of important applications, not just breaking secret codes, but also just doing calculations involving quantum mechanics. It turns out that for the same reasons why a quantum computer is powerful, quantum mechanical problems are hard. And if you had a quantum computer, then you could do certain kinds of quantum mechanical problems easily, problems that can't be done today. These issues that come up about quantum information go to the heart of some of these mysterious and fundamental aspects of quantum mechanics that I've been talking about. How is it that something can be in two places at the same time? How is it that an apparatus on the other side of the planet could be affected by what goes on in another similar apparatus on the other side of the planet? People have been wondering about these kinds of questions since people first started to think about these things in the 1930s. And so quantum computers address these same kinds of issues and may teach us something. It might be that the power of a quantum computer could solve general hard problems, and the implications for that are absolutely mind-boggling. Here's a statement that was made by a guy named Michael Friedman, a mathematician, a winner of the Fields Medal. The Fields Medal is sort of like the Nobel Prize for mathematics. And he said that if you had something like a quantum computer, and if it were capable of solving a certain kind of problem, that among its minor applications would be that it would supersede intelligent, even artificially intelligent proof finding with an not possessing or needing understanding. I don't even know what that means, but it sounds fantastic. And so people are really interested in this idea of quantum computing. Now there's another feature of quantum information that I want to talk about, and that is quantum communication. So let's think about how ordinary communication works. Now when we talk about communication, we always assume that we've got a sender who is A, who we call Alice, and there's another receiver, B, that we call Bob. And the idea in classical communication is Alice wants to send this piece of information, this 3-bit code, to Bob, and so she sends it along this line, and Bob receives it. Now, I always like to anthropomorphize Alice and Bob, but the real problem here for Alice and Bob is the possibility of eavesdropping. Now, you know this happens, right? People are wiretapping communications all the time. The National Security Agency in the United States probably has the capability of listening to every conversation that everybody is having. The problem is they can't process the information fast enough to learn anything useful. But that eavesdropper is somebody we call Eve. And of course, we can anthropomorphize Eve just as well. And Eve can tap the line and intercept the classical communication and do what evil things Eve, the eavesdropper, is up to. So that's classical communication. Now, let's imagine that Alice and Bob are quantum mechanical people. And so instead of sending classical bits, Alice makes this entangled state of spin up and spin down, and takes bit number 2 and sends it to Bob, who is also a quantum physicist. Now, there's no way of anybody knowing whether bit 2 is 0 or 1, and there's no way of anybody knowing whether bit 1 is 0 or 1, but once Alice measures bit 1 to be something, she knows for sure what Bob is going to find. Now, the trouble is that Eve, trying to tap this thing, isn't going to have any success. Because if she takes the qubit, she cannot produce a copy of it. There's a thing called a quantum no-cloning theorem, which is just a result of the uncertainty principle, that says you can't make a copy of an unknown quantum state. So she can't take the thing that Alice sent, send it on to Bob, and keep a copy for herself, and pretend to Bob that she's Alice and pretend to Alice that she's Bob. That simply isn't going to work because of the fundamental laws of quantum mechanics and Heisenberg's uncertainty principle. So if she tries, Alice and Bob will be able to tell. So Alice and Bob can establish a communication that they can guarantee is secure, that doesn't have an eavesdropper in it, just by applying the laws of physics. So this got a lot of people really interested. Okay, so now we have these 2 possible applications of quantum information. Quantum computers, which could factor numbers and do quantum mechanics problems. Quantum communication, which could allow you to transmit information that couldn't even be, whose code couldn't even be broken by a quantum computer. See, isn't this beautiful? You have quantum computers that can break the best codes we've got today, and then you've got quantum communication that could fix it so they won't. So we win either way, and the money just keeps coming in. So what are we going to use for these qubits? Qubits have to be something physical. I've been talking about them as if they were electrons, but in fact that's not the way most of them are going to work. A lot of them, especially the ones that we use for communication, are going to be photons, single particles of light. They could also be quantum dots. These are nanofabricated semiconductor devices. They could be what we call single Cooper pair boxes. These are superconducting metals where you can tell the difference between having one more or one less electron on the superconductor. And they can be in superpositions. Other superconducting devices called Josephson junctions can be qubits. Single atoms implanted in solids, and single isolated ions held in vacuum. These are the things that were talked about in that science fiction novel for some of the earliest experiments with quantum information, and what we do in my own laboratory, which is single isolated atoms, neutral atoms held in a vacuum. And there are even other ways that I just don't have time to talk about that you could make a quantum computer. So let me just give you a little bit of a feeling for how this would work for the thing that I love best, which is single atoms. So we have an atom here. So I've got a simplified version of the atom. There's a nucleus in the center. It's got a spin that points either up or down, and it's got an electron going around the outside. Remember, I told you that's a really bad picture of what an electron does, but I draw it just like everybody else. So there's this electron going around the atom, and it can either be spin up or spin down. And this configuration might be one energy state that we'll call 1, and the configuration where the electron is pointing the other way, that's the other one called 0, and the atom can be 1 or 0, so that's very nice, and it can also be both 0 and 1 at the same time. So these are the kinds of qubits that we work with in my laboratory, and to do a computation, well, you need to do logic. So when you do computer logic, you might add together two registers like this to get a new value. You add 5 and 1, and the last time I looked, that was 6. We do the same kind of thing with computer logic, with quantum computer logic. So your classical information processor, and those of you who are familiar with computers know that you can make a computer do anything if you've got single bit operations that can change a bit from being a 0 to a 1, and certain kind of universal 2-bit operations like ands or nands or ors that allow you to do any kind of a calculation. Well, it's the same way with quantum computing. If you've got certain kinds of single bit operations that can transform a single bit from one thing to a general superposition of 0 and 1, along with a 2-bit operation that will entangle the 2 bits together, then you can do any problem you want. So we've been working on making such devices in our laboratory, and I'm going to show you a little movie of where we start off with a whole bunch of atoms in what we call an optical lattice, just a regular array of places where we trap the atoms. And then we flip the spin of one of the atoms. So this is what I've shown here by turning that atom on the right to be red, and then we bring them together, and this entangles them, and that's the entangling operation. And so here's a movie, which I think I have to start by clicking over here, that's going to show how that actually works in the laboratory. So what we do is we first alter the lattice a little bit, so only one of the atoms is going to be affected by a field that we put in. Now we flip the spin of every other atom. Now we bring them together, and then they exchange their bits, and that entangles them. And if we stop halfway in between, then we've done what's called a square root of swap, halfway through swapping the information from one to the other, and that's an entangling gate that will be universal for quantum computing. And then we can dream about larger quantum computers, and here's a movie of our dream where we've got lots and lots of atoms stored in a 2-dimensional array, and we can change the state of any single one that we want to pick out, and then we can pick up individual ones of those atoms and move them to a place where we might work on them a little bit more. So there's a single atom that's been picked up, and another single atom had its state changed, and it gets picked up, and then we can operate on that pair of atoms in such a way as to, say, bring them together and entangle them. And this is the kind of process that we would do with hundreds or thousands or hundreds of thousands of atoms all at the same time. When is all of this going to work? Well, we've already got quantum computers using things like superconducting circuits and trapped ions that have something on the order of 10 qubits that can do all kinds of general operations. With a little bit more work, these small quantum processors could be made into what we call quantum repeaters, something that can allow us to transmit quantum information over very long distances. So that's coming really soon. A larger computer, one that could factor numbers that a regular computer can't factor, is going to be a lot longer. Maybe 20 years, maybe 50 years. In fact, I like to say that getting a quantum computer like that is sort of a 50-50 proposition. I think there's about a 50% chance it'll happen in 50 years. So this is something that is really a long-term goal, at least the way I see it. On the other hand, we can't see anything that's going to be preventing us from doing it. Now, it may just be so hard that people won't, that they'll give up, but we can't think of any physical laws that are going to prevent computers like this from being made. And quantum communication is already working. At NIST, we can transmit information fast enough that you could do streaming video with quantum information. And you can buy devices on the market that are a lot slower than what we have working at NIST. And quantum simulation of of interesting quantum problems using things that look like quantum computers is happening already. Well, I'm debating now whether I should tell you how this works, because it's a really cool story, but we're getting to the end of the hour. And so let me just tell you that in a beautiful experiment done by Ian Spielman and Trey Porto in our laboratories at NIST, he's shown that using this quantum simulation technique, which is very much like quantum computing, that he can solve a problem that nobody knew how to solve using ordinary computers, and verify an approximation method that some really clever people came up for solving this problem, and verify that that's the correct solution to the problem. So this really is an important step that's being repeated in laboratories all over the world, that we can solve quantum problems that we could not solve before simply because no computer was fast enough or big enough to do it before. And now we're doing it with quantum bits in the laboratory instead of with the kind of classical bits that make up ordinary computers. Now there's a whole lot of stuff that I've been hiding from you that's really important. I haven't told you very much about the physical platforms. I gave you a list of those physical platforms, but I didn't tell you much about them and about how hard it is to make them and about how hard it is to make a lot of qubits. I didn't tell you about the main reason why quantum information is so hard, quantum decoherence. This is the fact that every quantum bit is coupled to the rest of the world, and that coupling to the rest of the world messes up this beautiful superposition that we work so hard to create. And this wonderful feature of having a qubit in two different states at the same time is destroyed by having the qubit talk to the environment. And this is why we use something like single ions suspended in space, because this will slow down that coupling to the rest of the environment, but it never gets rid of it. And so in order to work in this dirty environment where our wonderful superposition states are being destroyed constantly, we have to do something called quantum error correction. And this is a wonderful idea, but it's also a horrible idea. What it means is that for every qubit you've got to have maybe a few hundred more qubits that allow you to do the error correction routine, and that you need an incredibly fast classical computer to take care of all the overhead to make that happen. So when I said a 300 qubit machine would be able to store more numbers than there are in the universe, well, more numbers than there are particles in the universe, well, you have to take that 300 and maybe multiply it by a few thousand. So it's not going to be so easy. And yet, we're working on it. And people are giving us a lot of money to do it. And people are making companies and selling stock in those companies and hiring lots of quantum physicists to do it. So this is a real thing that's really happening. And so I want to leave you with the thought that we are in the midst of a new quantum revolution with really unimaginably exciting promises, and that the future is looking bright. Thanks very much. Well, thank you very much, and I'm very happy to answer questions if there's time, and everyone who asks a question will get a prize. But it has to be a substantive question. That means you can't ask, what's the prize? You'll find that out when you get it. But so what it means is that I'm going to have to call on somebody, and I see a few willing people here who will distribute the prizes to anyone who asks. So I guess what we need is microphones for the people who ask questions, and I have to give the prizes, which I have here somewhere. Yes, here we go. So everyone who asks a question gets a prize, and after the first question, I will tell you what the prize is. So let's have a question. There's so many people. and I can't see them. So somebody figure out who's getting the question, and then I'll give you the prize, and I'll tell you what it is. Okay, what's the question?
You remember when Alice was talking to Bob?
Yeah.
I don't understand how they can communicate if even Alice don't know what she sent to Bob.
Ah, yeah, right. Okay, so that's part of the stuff that I left out. So let's go back to Alice and Bob. If I can find my cursor. It's here somewhere. Okay, there it is. Now I got it. Okay.
And I have a second part of the question. If Alice can send information to Bob, that doesn't break causality because it goes immediately one to other.
Yeah, yeah. So okay, both very good questions. Okay, so Alice sends the information to Bob, and she doesn't know what it's going to be, and she doesn't know what her bid is going to be. But when they measure it, they both know. Now, the thing that I didn't tell you, because I was hiding lots of stuff. I told you I was going to commit a lot of sins. What I didn't tell you is this really isn't the process of sending information. This is the process of distributing the key for a code that they're going to use later to transmit information. So in the old days, you would send somebody with a briefcase full of a code book, and the briefcase would be handcuffed to his wrist, and then he would deliver the suitcase to some diplomatic agent somewhere on the other side of the world. Now you can do it without sending somebody with a briefcase, and so that's how they're transmitting not the information, not the message, but the code they're going to use later to transmit the message. So another thing I didn't tell you was that they have to communicate along an open classical channel in order to make this work. So in other words, Alice says, okay, you remember that first qubit I sent you? And Bob says, yeah, got it. She says, okay, since you got it, let's make that the first bit of our code book. And Bob says, great. And they do this in the open, and Eve can listen to that conversation, but she can't do anything about it because she doesn't know what the numbers are. But Bob and Alice both know what the numbers are. So that's how it works. Now, causality. It turns out that this instant existence of information is not the same as instant transfer of information. So instantly, when you know what the value is at Alice, you instantly know what the volume is at Bob, but Alice hasn't transmitted any information. The exact point that you saw in the first part of your question. It's only later that they're going to transmit information. They take whatever they get and make that part of their code book. Now, the thing you got two cards. One is the wallet card of the fundamental constants of nature. Now, why have I given you that? Because, of course, first of all, everybody wants to know the value of the speed of light, Newton's constant of gravity, Planck's constant, the charge on the electron, it's all here. And at NIST, we own the fundamental constants, by which I mean we have the responsibility of coming up with the best values based on the information that people send us from all over the world about their latest measurements. So I like to give these out. The other thing is a list of the defining constants of the International System of Units. On May 20th of next year, we are going to have the biggest revolution in the system of measurement units. The meter, the kilogram, the second, the ampere, the Kelvin. We're going to have the biggest revolution in that system since the French Revolution. And this card tells you what that revolution is all about. Okay, let's have another question.
Thank you.
Here, why David Bohm version on your slide? What do you think concerning David Bohm interpretation of quantum mechanics?
Yeah, okay, so in fact it has nothing to do with, let's see, I got to get back to Bohm. It has nothing to do with Bohm. Oh, I'm going the wrong way. Sorry about that. Okay, okay, look, it doesn't matter. It has nothing to do with Bohm's interpretation of quantum mechanics, which is a little bit weird. He makes the wave function be a kind of hidden variable. He came up with an interpretation of the Einstein-Podolsky-Rosen paradox. So Einstein, Podolsky, and Rosen in 1935 came up with this idea for basically questioning the completeness of quantum mechanics. Imagine that you had two entangled particles, that you would measure the momentum of one and you'd measure the position of the other, and it appeared to violate the uncertainty principle. Well, Bohm reformulated that problem in terms of spins, and that's the thing that I presented. So that's why Bohm's name was on that, because of the reformulation of the Einstein-Podolsky-Rosen. So it has nothing to do with Bohm's interpretation of quantum mechanics, which is another thing entirely, and interpretations of quantum mechanics, well, you know, they are what they are. Okay, more questions and more prizes. So why don't I just give you this stack of, okay. So who's next? Okay, we'll just start talking and I'll listen.
Sí, yo tengo una pregunta. How can two things can be in the same place and the same time?
Yeah, well, okay. Well, for me, the thing that's hard is to have one thing in two places at the same time. Is that what you meant?
Yes.
Okay, good. How can that happen? I have no idea. I don't think anybody has any understanding of how that's possible. All we can tell you is what it means. So let me expand on the idea of something being in two places at the same time. So let's say I prepare, and I can, in fact, we do this all the time in the laboratory. Let me prepare a state of one atom that is both here and here. Now, what does it mean for that to be true? It means that when I measure it, I'll measure it to either be here or here. Now, that's not enough, because you could say, look, I just flip a coin and it's in one or the other. That doesn't make it in both places at the same time. And you're right. So there's another part. There is something I can do to that state, which I know will half the time put the particle here and half the time put the particle here. There's something I can do to it, and I know exactly what it is, that will make it so that after I do that thing to it, like I shine some light on it, that every time I measure it, the particle will be here. In other words, that state that would produce half here and half there, there's something I can do to it, and I know exactly what that something is, that'll make it so there's always here. That's what I mean operationally by having something that's in two places at the same time. Now, some people object to that language of saying that it's in two places at the same time, because after all, what really counts is what do I measure, and I've just described in a little bit more detail what I would measure. I like the language that says it's in two places at the same time, but I have colleagues who find that language distasteful. It's just a matter of your preference for how you like to describe things. We know what the mathematics means, and I don't think anybody really understands it in their gut. One of the famous physicists of the 20th century, Richard Feynman, said, if you can't explain something to a high school student, then you don't understand it yourself. He also said, nobody understands quantum mechanics. So,
This one is at the left or the...
okay, and don't forget this lady here. Yes.
Good afternoon, Professor. My question is about the superconducting circuits. I mean the Josephson junction circuits. I didn't understand really good how are they related with the quantum computers, and I would like to know also if those circuits already exist physically, or they are just theoretical.
Yeah. Okay, good. The reason you didn't understand it was because I didn't explain it. so your question is a very good one. Now, okay, I'll try to give you a simple explanation of how a Josephson junction works in a circuit. Let's imagine that I have a loop of superconducting wire, and I can put current in that superconducting wire, and that current cannot be just any value of the current, it has to be a specific value. It's sort of like the spin can only be up or down. The current in this wire can only be certain values of the current. Now I break that circuit with a thin layer of insulation. And it turns out that if that thing is thin enough, the current can still go through it. But now things are a little bit different. And because of the existence of that thin layer of insulation, I can manipulate the circuit more easily, and I can put it into one of these superpositions rather easily. A superposition of, say, having current and not having current, or having current going one way and having current go the opposite way. So now it becomes a qubit. Now, your question is, do these things exist? Yes. In laboratories, actually laboratories operated by Google in Santa Barbara, California, in laboratories in Yale University in Connecticut, in laboratories at IBM, they have small quantum computers that work this way. And in fact, you can go online and you can propose a problem for the quantum computer to solve. And they will go in and do that problem and send you back the results. They work really, really badly. That is, most of the time they fail. But every once in a while they work, and they give you an answer that you could have easily calculated on your laptop. So, what I'm telling you is, yes, these quantum computers exist. They're not good enough to do anything interesting yet, but it's a start. And, you know, maybe in another 10 years, these things will do problems that we can't do on our laptops. We'll see. So, well, I want to take your questions, but you have to have a microphone.
The next
So,
question is
Hi.
okay.
at the back. There is-
Right, okay.
Due to the small scale of the quantum realm, how do you maximize the precision of the measuring of the state of the particle? Well, like, what processes do you undergo in order to maximize that precision of the reading of the state, if it's up or down?
Okay, I'm not sure I understood the question. My ears, my old ears are not quite as good. Can you couldn't, okay, maybe you could repeat it, but with your mouth a little bit further from the microphone.
Like,
Okay, so she's saying if you would like to repeat the question in Spanish, she'll translate it for me.
is it like this? Maybe like this? Okay, like, what processes do you undergo in order to maximize the precision of the reading of the state, if it's up or down in the particle?
Ah, okay. So let's say that I've created a state that is a superposition of up and down. I have the freedom in the laboratory to make that superposition anything I want. I can make it half up and half down, in which case, when I measure it, I will have a completely random result of sometimes up, sometimes down, just like flipping a coin. On the other hand, I'm free to create a state that is 10% up and 90% down. And if I do that, when I measure it, it will be 10% of the time up and 90% of the time down. There isn't anything in the measurement that I can do that will determine whether it's up or down. Now, maybe what you meant was what I talked about, that there's another process I can perform. And that process that I can perform can make it always up or always down. So let me tell you how that would work. Let's say I take a spin and I shine some microwaves at that spin in such a way that it is now in a superposition of being up or down. If I keep track of the phase of the microwaves, I can give it another burst of microwaves at just the right time, with just the right phase, that'll make it go all up or all down. So that's an example of how I could prove that it was really in a superposition. And we do that all the time. That's how atomic clocks work. So that process of maximizing that it's going to be spin up or spin down is something that is routine in atomic clocks. So it really is something that's a real thing. The last question, oh, what a sad thing, but
I'm sorry, I know that you say that the question of time, you don't explain the equation, but I have some curiosity about the equation.
which equation?
It's in the,
Okay, well, tell me, maybe I can find the slide. What was in the equation, or what else was on the slide?
it's because, I don't know.
Okay, let me, I'll just go through them and see. Okay. Are you seeing anything you like? I think we're almost out of equations. That one. Oh, you picked the most complicated equation I've got. Okay, okay, good question. Okay, so what we're doing here is this is a Hamiltonian that is often used to try to describe the way electrons move in a crystal. And the idea is that this term here tells how easy it is for an electron to tunnel from one atom to another in the crystal. And this term, if I can do it, the second one, the one with the U, here we are, this one. This term tells you how much energy it costs to have two electrons sitting on the same atom. So these are very simple ideas. How fast does an atom tunnel from one to the next? And how much energy does it cost to have two electrons on the same atom? And it turns out you can prove that the whole behavior of the system only depends on the ratio of those two things. So what could be easier? You got one number, the ratio of those two values, and that is explaining everything. And nobody can solve this problem if you've got more than about 30 lattice sites, because the difficulty of solving the problem doubles every time you add one more lattice site. So that's why we want to have another way of solving it. And the other way of solving it is let the atoms do it. Make an array of atoms that can tunnel and that have an energy cost to be on the same site, and then just see what happens. And that's exactly what happened in this experiment. We had a bunch of atoms and a bunch of lattice sites, and changed the ratio of those two parameters, and that changed the state from being one where the atoms are uniformly distributed across all of the sites to one where they're pinned on individual sites, and the place where that happens very sharply. You see it goes boom, and then the atoms are pinned. And knowing where that happened, nobody knew where that was. And we were able to measure it, and other people were able to do an approximate calculation, and they agreed. And that made us all very happy.
And another little question. What's your opinion about the thing of the Riemann hypothesis?
Ah, the Riemann hypothesis. Well, as it turns out, I was in the audience when the talk about the Riemann hypothesis was given. And the first part of the proof for the Riemann hypothesis involved calculating the fine structure constant. And then, having the fine structure constant, then he proved in a few lines the Riemann hypothesis. Now, I've been around a long time, not as long as he has, but I've been around a long time, and ever since I was really small, I was seeing people claim that they could calculate the fine structure constant. Okay, and all we had to do then was measure the fine structure constant a little bit better, and it turned out, no, they hadn't calculated the fine structure constant. They just put a bunch of numbers together to give the value the fine structure constant had as best we knew it at the time. So I'm skeptical. That's my answer. I'm skeptical.
Thank you.
Sure.